All right. Find two positive numbers whose product is 192 and whose sum is a minimum. So even though we say optimization, and usually you think about optimization as creating the most or the best of a situation, right? Minimum still falls into that category. So we are finding the minimum of a sum. That's maybe the most important part to this process, is trying to identify what it is we're trying to minimize or maximize. So what are we minimizing? A sum. The sum of what? Two positive numbers whose product is 192. So this really takes on the form of a system of equations. And when you learned this the first time, which was probably in algebra, it was under that category of system of equations, but we would graph it. We would find wherever the maximum was or wherever the minimum was. Okay. We are taking the calculus approach, which is you can find the minimum by setting the derivative of a statement equal to 0 and then solving for x, right? Because that's where the minima and maxima occur. They occur at those critical points. We just need to be able to write the statement that we're trying to minimize, and that statement will be the sum of two numbers, okay? So if I'm just like, yeah, okay, I need to minimize this, because I don't know what those two numbers are. How are we going to minimize this statement, right? Again, do we want to do implicit differentiation? We really don't. Okay. So instead, we take this first piece of information where they say whose product is 192. So I know that the product of these numbers is 192. I'm trying to minimize their sum. Okay. In order to minimize this, as I just said, we want to find the derivative and set it equal to 0. But differentiating for x and y, no fun. We come back to this equation. We say, what if I solved for y in terms of x, right? I think everybody's pretty much comfortable differentiating with respect to x. So we solve for y in terms of x. Then we take that statement, or that value, should I say, and we plug it in over here. Now I'm going to centralize this whole statement and say that the sum of these numbers then would look like this. So this is what I am trying to maximize. So I'm going to take the derivative of this with respect to x and set it equal to 0. In order to do that, okay, it would make sense, I think, to rewrite this so that that x is not underneath the 192, right? Then we can just use the power rule as we're differentiating this. So we get the sum is 1, as we start to take the derivative, my fault. As we start to take the derivative, we're taking the derivative of this sum with respect to x. Okay, so we take the derivative of x, which is just 1. Now, when we differentiate this, we multiply that negative 1 in front, subtract 1 from the top, and we end up with that. Okay, so this is our derivative. If we set this derivative equal to 0, I'm going to do this now. Okay, because if I do that, having a negative exponent in here can be kind of confusing when it comes to solving for x, right? But when we look at this statement, we've got this x squared that's on the bottom. Okay, we've got any number of ways that we could go about solving this. Here's what I would propose. There's this concept that we've talked about before where in the simplest form, if I ever have a variable that's on the bottom of a fraction, if I can isolate that variable in the denominator, I can just switch it with what's over here. Call that the switcheroo. Same thing applies even if it's squared. So the first thing I'm going to do is subtract 1 over to the other side. So I've got negative 192 over x squared equals negative 1. And then I'm going to swap these values out. Okay. So I end up with, when I move the negative 1 down to here and the x squared out, that's going to be a negative over a negative. And it's just 192 over 1. So that's x squared equals 192. Take the square root of both sides. And we've got this. Now, you should know that when we take the square root of something, we're supposed to include positive and negative outputs for that. But take a look at the conditions of the problem. These numbers that I get for x and y have to be positive numbers. So I'm not even going to bother putting the plus or minus there because I'm not supposed to include the negative output for that. Okay, so this is our value of x. And as I said in a previous video, that's not the minimum sum. That's the value of x that produces the minimum sum, right? So I know what my x value is. Now I need to figure out what my y value is. Now, 192, okay, is not a perfect square. It houses a perfect square. It has a perfect square factor. And you know, since this is a calculus video, I'm not going to drag you through the mud of simplifying that radical, okay? But there's a 64 in there. So 192 is 64 times 3. Square root of 64 is 8. So in its simplified form, 192 is 8 over radical 3, okay? Keep that in the back of your mind. So we have this value for x. So our value for y, as we showed up here, y is equal to 192 over this, okay? If you did the square root of 192, I mean, actually, that might actually be cleaner, but we're already here. So this would be our value for y. If you said this is our value of y and you just wanted to move on, I wouldn't blame you, but again, we're going to rationalize this. So we're going to multiply by radical 3 on the top and bottom. So we get y equals 192 radical 3 over 24. 192 over 24. Yeah, I'm going to cheat here. Is 8. How about that? Awesome. So 192 over 24 is 8. So what do we get? We get 8 radical 3. So our values of x and y are actually the same. So the sum as a minimum would be, so again, our sum that we are trying to minimize is 8 radical 3 plus 8 radical 3 for a total of 16 radical 3. So this is our minimum sum for two numbers whose product is 192.